Okay, so now that we have a bit of our understanding of mixed strategy Nash equilibria as well as pure strategy Nash equilibria, let's talk a little bit about what we can say about existence of equilibria, what they look like, when there are more than one, and what some of the comparative statics are. So in particular, let's get started by looking at some comparative statics of mixed Nash equilibria. And in particular, let's ask the question, suppose we change the payoffs of one of the players, how do the equilibrium strategies that the players employ change as a result of that? This is pretty easily illustrated in a classic example, which is known as a war of attrition. And in a war of attrition, we have two players, say two companies that are in a declining industry. There's only room for one company, and they can either stay in or exit. So there's positive profits if one stays in and the other exits, but there's negative profits if they both stay in. So basically they're playing a waiting game, hoping that the other one will leave first. They can stay in the industry and enjoy some profits. So let's have a look at a simple version of this game. So in particular, let's just suppose that we think of a game where there's two players. They can choose to either stay or leave. If they both stay, they get a negative payoff, say -2 each. So we have the first cell here, they get -2 each if they both stay. If, say, the row player leaves and the column player stays, then the column player is going to get a positive payoff of 1, and the row player now gets 0. So once you leave, you get 0 no matter what happens by the other player, but once a player leaves, if the other player stays, then they get a positive payoff. So you'd like to be the person staying with the other person leaving. Well, in this game, it's pretty easy to see that there's multiplicity of equilibria. So in particular, in this example, what do we see? We see that there are two pure strategy Nash equilibria, one where the row player leaves and the column player stays, and so the column player enjoys the positive payoff of 1. And the other, which is the symmetric version of that, the row player stays and the column player leaves, and then it's the row player that's getting the benefits. Okay, so two pure strategy Nash equilibria. There's also one mixed strategy Nash equilibrium. So let's look at that equilibrium. In particular, I suppose that the row company plays stay with a probability PR, and the column player plays stay with a probability PC. So we've got PR and PC being the probabilities of the row and column players staying. So what has to be true in a Nash equilibrium? In a Nash equilibrium, say the row player needs to be indifferent in order to play both strategies. If they leave, what are they getting? They're getting 0 no matter what. So payoff to leave is 0. If they stay, they're getting -2 if the column player stays. Column player staying with probability PC, so they expect -2 with probability PC, and they get a positive payoff of 1 if the column player leaves. Column player is leaving with probability 1 minus PC, so they're getting a payoff of essentially 1 times 1 minus PC, so their overall payoff is -2 times PC plus 1 minus PC. Okay? So in order for them to be indifferent, it has to be that the payoff from the two strategies is equal. So the payoff from staying is equal to the payoff from leaving. And if you solve that for PC, it's pretty easy to see that PC is going to be 1/3. So in a mixed strategy Nash equilibrium, the column player is staying with probability 1/3, leaving with probability 2/3. You do the same calculation for the row player staying and leaving, and the column player being indifferent. Given the symmetry in this, it's pretty easy to see you're going to get exactly the same solution. So you're going to have 1/3 probability stay for the row player, 2/3 that they leave. So what do we end up with? We end up with 3 different equilibria. One where one of the players stays and the other one leaves. There's 2 such equilibria, and then the mixed strategy equilibrium. So here we have 1 mixed strategy equilibrium and 2 pure strategy equilibrium. 2 pure strategy equilibria. Okay, so that gives us an idea of what the equilibria look like. Now let's suppose that we make the row player, the company, more profitable. So instead of having a 1 in this cell, let's put a payoff of x, where x is possibly greater than 1. Okay, let's go back, resolve this. So in terms of the pure strategy equilibria, nothing's changed. There's still a one equilibrium where the row player stays, the column player stays and the row player leaves. There's correspondingly one where the row player stays and the column player leaves. So we have the two pure strategy equilibria. Those are still equilibria. But let's look at what happens to the mixed strategy equilibrium. So in order to have a mixed strategy equilibrium, again, each player has to be indifferent between playing the two different strategies that they're mixing over. So here we have the row player needs to be indifferent in order to play both strategies. So here now the payoff to staying for the row player, so actually the payoff to leaving is still 0, right? If they leave, they still get 0 no matter what. If they stay, if we're putting in probability PC that the column player stays, 1 minus PC that the column player leaves, we're getting -2 with probability PC, and x with probability 1 minus PC. So the payoff to staying for the row player is this expression here, -2 times PC plus x times 1 minus PC. So we set these two payoffs equal to each other. So this payoff has to be equal to this one. And what does that give us? That gives us this equation. We solve that for PC. If you solve that for PC, what are you going to get? PC here is going to be equal to x over 2 plus x. Okay, so we have a mixed strategy equilibrium. In the case where x was equal to 1, if we had our x equals 1, then PC was equal to 1/3. That's a good check. So we're getting the same answer we had before if we plugged the 1 back in. But what happens for other payoffs? So for instance, if we set x to be bigger than 1, then x over 2 plus x is actually greater than 1/3. So instead of 1/3, they're going to be putting higher probability, the column player will be putting probability of greater than 1/3 on stay in the case where x is bigger than 1/3. And in particular, just to get a feeling for this, let's suppose that we put in the x equals 3 and solve to see what we end up with. In this case, again, we have two pure strategy equilibria. And now the mixed strategy equilibrium. Remember that the column player is staying with PC is equal to x over 2 plus x. If we plug in 3 for x, this is equal to 3/5. So what happens here? Now we've got the column player staying in with probability 3/5. The row player is still going to stay in with probability 1/3. So the column player's strategy payoffs haven't changed in terms of their payoffs of -2, 0, 1, 0. So when you make the column player indifferent, it's exactly the same equations that we had before. So the row player's probability to make the column player indifferent is exactly the same as it was before, but we're getting a different answer for what the column player has to do in order to make the row player indifferent. So we end up with the column player staying with higher probability than before, even though it's the row player's payoff which has gone up from staying. Right? So in terms of the subtleties of mixed strategy Nash equilibria, when we look at these comparative statics, what we did is we made the row player have a higher payoff to staying when the column player leaves, and yet it's sort of the weaker player, the one that's getting a lower profit, who ends up staying with higher probability. So making the row player stronger means that the column player ends up staying with higher probability in order to make the row player indifferent. So here, one player's strategy, how they mix, is determined by making the other player indifferent. So what the column player is doing is adjusting to the row player's payoffs, and conversely, the row player's mixture is adjusting to the column player's payoffs. So here we need the stronger player to be indifferent. That means that the weaker player ends up staying longer. So there's some interesting comparative statics, and this is the kind of thing that gives us an idea of why game theory is an important tool, because this is something that superficially one might get wrong if you didn't actually go through and understand what the comparative statics actually look like. One might somehow believe that the stronger player should just stay with higher probability. So the game theory here gives some insight that we might not have otherwise.